All right, everyone. Thanks for coming back after lunch. We're ready to begin our next session, and our first speaker is Feige, who'll be speaking about the effect of randomness on planted recoloring.
So good afternoon. This is joint work with my PhD student, Roy David. So I'll be talking about recoloring. We all know this problem. The input to the problem is a graph, and the desired output is a coloring of the vertices of the graph by 3 colors, such that every edge has 2 different colors in its endpoints. As we know, recoloring is NP-hard, and so we are interested in considering a framework that will help us recognize some easier instances of this NP-hard problem. And the framework that I will describe here can be applied to other problems as well. So what we will consider is the framework that we call the hosted coloring framework. And in generating an input within this framework, we have 2 choices to make. One is some host graph H. And then within this host graph H, we plant some coloring P, which is, what does it mean to plant a coloring P? We partition the vertices, let's say, into 3 groups, and each group is a color class. And the input graph G to the problem is obtained by removing from H those edges that violate the legal coloring property, the monochromatic edges. So as an example, let's say this was the host graph H. We plant in it some arbitrary coloring. It's not necessarily legal. So there are certain edges which are not legally colored. We see which are these monochromatic edges, and we remove them. Then we remove also the colors from the vertices, and we give this graph as input to the algorithm. So this is the general framework. And the algorithmic challenge is the following. We get G as the input graph. The algorithm never sees the original graph H or the planted coloring P. And the goal for the algorithm is to legally recolor this graph G in polynomial time. Now, I should emphasize here that G may have several legal free colorings. The planted coloring is not necessarily the unique coloring in this setting. So you are allowed to output any legal free coloring. You don't have to find the planted one. So within this model, within this framework, we can have several different models. And here's one which was studied extensively. Sorry, I'm not there yet. So like this is really one that was studied extensively. Okay. So the host graph is adversarial, and the planted coloring is adversarial. In this, let's say, specific case, then there's nothing you can do. It's just a worst case instance. So the problem is NP-hard. But there are other variations of the model. So depending on how we choose H and P, the problem can be easy or difficult. So a model that was studied and described in previous talks here is the random planted recoloring model. So in this case, the host graph, one way of viewing this model, it's not always the way in which this model is described, but that's an equivalent way of describing it. In this, you can think of the host graph as a random G and P graph. So each edge there is present independently with probability P, and there are n vertices. And the planted coloring is random in the sense that every vertex gets at random one of 3 colors, and then you remove the monochromatic edges. So this model is equivalent to what is known as the GNPK model, or K in this case is 3, that was studied before, of random K colorable graphs in which there are K color classes, and you just place the edges between the color classes within a probability P. We'll use the notation instead of P for the edge probability. We'd find it more convenient to look at, to use the notation G and D, where D is the average degree of the graph, because it's a bit more informative to look at it in terms of the degree and not the probability of the edge, but it's interchangeable. So our random version can be denoted as G and D3 in our case. And D means that we have a random graph of average degree, roughly D. So there were many works in this model, and the strongest result known is this result of Alon and Kahale. So what they described as partitioning into two theorems. So the first is that they show that a spectral algorithm finds the planted recoloring P whenever the average degree that you start with is large enough, larger than a constant times log n. And the second is that even at smaller values of d, and in this case, the planted coloring P is no longer the unique free coloring of the graph. There would be other legal free colorings. A polynomial time algorithm can find the legal free coloring provided that the initial degree is large enough, a large enough constant. So this algorithm starts with the spectral algorithm, but then has additional steps afterwards. So the spectral algorithm by itself would not recover the coloring here. And all the results, these results, of course, hold, since it's a random model, so they hold almost surely for random choice of G and P. So you might be unlucky and choose a graph on which it fails, but with high probability, the algorithm would work. On most graphs, it will work. So the questions that we ask ourselves is which aspects of randomness are really needed for the Alon-Kahale results. So does the host graph really need to be random, or can we replace it by some deterministic maybe choice of graph? The family of graphs, let's say graphs with high expansion, would that be enough? And the other question is, does the planted coloring have to be random? Is it okay if we let the adversary maybe look at the host graph and partition it into 3 equal size color classes, but he can choose which vertex goes into which color class? Does this really make a difference? So the outline of this talk is that I'll first review the algorithm of Alon and Kahale and sketch how it is analyzed, a very rough sketch. Then I'll describe what changes when the host graph is an expander chosen by an adversary. It's no longer a random graph. Consider also what changes when the planted coloring is also chosen by an adversary, and then present some open questions. So to present the results, to understand them better, it's good to keep in mind the following notions of coloring. So P is the planted coloring that we have. Now we'll have a notion of a B approximate coloring. So this is a coloring which is not necessarily legal, but it agrees with the planted coloring almost everywhere. Only B vertices are colored differently than the planted coloring. So it's a coloring which is not necessarily legal, but of small Hamming distance from the true planted coloring. A safe B coloring is something even stronger. So in that coloring, you don't color the whole graph. You color all vertices except for B vertices. All these vertices are colored exactly as in the planted coloring, and the remaining vertices are just left uncolored. They are free. So you know for sure that whatever you colored exactly as in the planted coloring. About the rest, you don't know what to do. And the legal coloring is any coloring that legally colors the whole graph, not necessarily the planted coloring. Another thing that would be helpful in understanding the algorithms is the notion of good and bad vertices. So let's suppose we have the host graph is roughly D regular. D can be also a function of n, so think of it square root n regular is also okay. And we have a planted free coloring P. So if the coloring was random, then typically every vertex has 1/3 of its neighbors in each of the color classes. And then the edges connecting it to vertices in its own color class are removed. So if this was the situation, we refer to this vertex as good. And if this was not the situation, we refer to the vertex as bad. And it's not hard to see that if P is a random coloring, it doesn't matter if the host graph is random or not, but if P is a random planted coloring, then almost all vertices are going to be good. The fraction of bad vertices is exponentially small in D. In particular, if D is larger than log n, there are no bad vertices. Okay. So now we can describe the Alon-Kahale algorithm. So it has several steps. The first step starts with a spectral clustering. I'll say a few words about it later. And after this stage, what you have is an approximate coloring. So most vertices are colored exactly as in the planted coloring, and some small fraction, n over d, 1 over d fraction, are colored differently, and this is also not a legal coloring. Then, then we have a local improvement step that I'll describe as well. It still gives an approximate coloring, but it reduces the fraction of colors that are not colored according to the planted coloring. Now it's only order of b. In particular, if the degree was larger than log n, you finished now at this stage, because b, at that case, is smaller than 1. So you'd get just the planted coloring. But if d is a constant, you're not done. The step after that is some cautious uncoloring. Any vertex that looks suspicious for some reason, for example, it participates in some illegally colored edge, might be a good reason to suspect that something is wrong with it, is just uncolored. And what you get after this stage is, if you do the uncoloring cleverly, is that you have a safe order B partial coloring. So almost all the graph is colored and colored exactly as in the planted coloring, and a few vertices are left uncolored. And the last stage, because the number of vertices which are left uncolored is small, you can finish off and coloring the rest of the vertices using some dynamic programming algorithm, essentially going over all possibilities in some clever way. So let me give a few more details, and really very briefly. So the first step is a spectral coloring. So if we consider the eigenvalues of the adjacency matrix of the input graph G, we look at the two most negative eigenvalues, and we look at the eigenvectors that correspond to them. Each vertex has an entry in each eigenvector. So this gives an embedding of all vertices in the plane according to their entries. One coordinate is their entry in one eigenvector, the other in the other. And you cluster according to distances in this embedding in the plane. And you get from these three color classes, which are not necessarily legal coloring. You might have edges within a color class. And the theorem says that this approach gives this order n over the approximate coloring. So in a picture, what is this coloring? So this is like schematically the whole graph, and the green regions are those colored exactly as in the planted coloring, and there are some red regions where the coloring is different than the planted coloring. Doesn't mean that it's an illegal coloring. Maybe part of it can still be completed to a legal coloring, but different than the planted one. The next step is a local improvement. So each vertex can look locally and see if it's colored, if there is some color class in which it has fewer neighbors than its current color class. And if yes, it wants to switch to that other color class because the coloring would look more legal this way. So you perform these local improvement steps, and there's a theorem showing that, after you do this, the fraction of vertices in which you differ from the planted coloring becomes much, much smaller. So in the picture, we started with this picture, and the red regions shrunk by a lot. The next step is the cautious uncoloring. So we suspect that something is wrong with a vertex if it has fewer than d over 6 neighbors in one of the other classes. So maybe it should have been in the other classes because there's only few neighbors in that other color class. We're not sure about it, so we simply uncolor it. So now it has no color, it becomes free. And the theorem says is that we don't need to do it for too many vertices, and once we do it, the coloring that remains is safe. Every vertex that still maintains its color, it's because it has exactly the same color as in the planted coloring. That's the only reason why a vertex maintained its color, and almost all vertices did it. So we start with this stage with an approximate coloring, and what we do we do some uncoloring, so some vertices lost their color, and everything else is colored exactly according to the planted coloring. And the last stage is dynamic programming. We have to show that we can finish off the coloring now. So we have the safe partial coloring. Almost everything is colored. We have small regions which are uncolored. And a key lemma there is that it's not just the number of vertices that are not colored can be, let's say if D is constant, can even be linear in N. So there might be a lot of vertices not colored, but the main theorem here is that these vertices which are, if I look at the graph induced on just the vertices which are not colored, it decomposes into small connected components, each of size not larger than log n. And hence, on each component, I can do exhaustive search and color it, and it's isolated from the rest of the components. So I can eventually color the whole graph and complete the coloring. So this is a sketch of the algorithm of Alon-Kahale. So the end really is the following. We started with this safe coloring, and you completed it to a legal coloring, and this legal coloring no longer has to agree with the planted coloring. So these regions, I colored them legally, not necessarily exactly the same as the planted coloring. So a summary of the algorithm, the first step was this spectral clustering that gave an approximate coloring, then some local improvements which gave a better approximate coloring, then a cautious uncoloring that gave a safe coloring, which is a better notion than approximate coloring because we make no errors there. And then we finish with dynamic programming. So now we reach the topic of this talk. So where did we use randomness in this algorithm? So one question is, does the host graph need to be a random graph? And the first step in the algorithm, the spectral clustering uses facts about the spectrum of the graph, about eigenvalues. If we look at the analysis of the other steps, the local improvement step, for example, it uses the fact that H, the original graph, had high expansion. Both these things are captured by requiring that the host graph be an expander, and a way of measuring the quality of an expansion is usually by the second largest eigenvalue of the adjacency matrix. So a natural question to ask is, suppose that we allow the adversary to choose a host graph whatever in any way he wants, as long as the second largest eigenvalue is small. So let's say smaller than the largest eigenvalue would be D in this case, and the second largest value, let's say smaller than D over 30. And then P, the planted coloring, is random. Can we still recolor such graphs? So that's the question that we asked. And the algorithm that we run is basically the same algorithm. Okay? And the question is, would it work? Start with a planted spectral coloring, local improvement, cautious uncoloring, and dynamic programming. At the end, would the same thing just to work as it is? So our algorithm follows the same step. It turns out that we need to change some of the details of some of the steps, and we need to change the analysis in some places. And one of the reasons we cannot use anywhere in the analysis the randomness of the host graph. And another reason is that the expansion that we have here is not as good as that of random graphs, so it makes the analysis more difficult, but basically everything goes through. So the one most interesting maybe step that changes in the analysis is the last step, going from the safe partial coloring, completing it using dynamic programming. So that's the one step, I think, where the difference is maybe more significant. If we look at perhaps the most complicated technical part of the paper of Alon-Kahale was to show that in this step, each connected component of uncolored vertices is small, of size order of log n. This was not an easy proof. And we circumvent the need to prove such a thing because in our setting it's even more difficult to prove it. So really what we show that even if connected components of free vertices have arbitrary sizes, we can still complete the partial coloring to a legal one. And the reason why we can do it is because we add one more step to the algorithm, which is safe recoloring. It's an obvious thing to do. The point is to show in the analysis that it really helps. So if a vertex V that we have in the safe coloring has neighbors in 2 different colors, then you know what its own color has to be. It has to be of the 3rd color. So just color these vertices that you know their color. And what we can show is that the point is the analysis, not the algorithm. The algorithm is in a sense obvious, that once you do finish this safe recoloring step, then indeed the connected components are small. And then you can finish using dynamic programming. And our proof here uses only randomness of the planted recoloring, and the host graph does not need to be random. It's enough that it's an expander. So the proof, in fact, if the expansion is as good as that of random graphs, in the sense that the second eigenvalue is order of square root t, the proof is quite easy, relatively easy, a counting argument. But if the expansion is not so good, then the proof becomes, let's say, more interesting. So this part of the work that I described before more or less showed that whatever worked for when you have a host graph which is a random graph, essentially all you needed was expansion, and you can modify the algorithm to work. The other question that we ask ourselves is whether the planted coloring has to be random as well. So the model is as follows. First, the host graph is selected. Then after yes?
I'm sorry, it's a sort of a high-level question, right? So in a lot of the spectral algorithms, the cleanup phase is what really uses local randomness. The that's what's happening here, right? The last but one step, everything uses only spectral properties rather than randomness. Is that sort of a gist of what, just sort of understanding your stuff?
So, in a sense, what we are saying, so if you look at randomness of the host graph is where it is needed, so it was needed, as I said, basically for 2 properties. One is to show that it doesn't have negative eigenvalues which are too negative, and hence the spectral technique finds something correlated with the coloring. And then to build upon it, we used expansion in many of the arguments. And really what this says is that you didn't need much more. That essentially both these things are captured just by expansion, and you never really needed the randomness.
So is that also possibly true of planted partition and other things?
We didn't look at it yet. Okay.
All but getting epsilon fraction right, you can do just with
yes. So we'll see now what happens here, which is a somewhat different picture. So does the planted coloring need to be random? So the model is the following. There's some host graph. The adversary looks at the host graph and chooses 3 color classes, all of roughly the same size, and remove the monochromatic edges. And this is the input. So he can see the graph and then do his choices. Does this matter? So what changes? So one thing that changes by a lot is this notion of good and bad vertices that we had before. Before we said that the fraction of bad vertices, those that don't see roughly 1/3 of their neighbors in each color class, is exponentially small in D. Now it's much larger, but it's still rather small. So what we can show is that the number of bad vertices, not as good as it was before, but it's depends on what the second largest eigenvalue is, but it's somewhat smaller than n. Most vertices are still good, but a sizable fraction of them are bad. This is something that changes and would cause problems for us. So the algorithm, we have, again, the same general scheme as before. Now here I'm looking at the case where the host graph is an adversarial expander, and the planted coloring is also adversarial. There's no randomness at all in this model now. Everything is deterministic, and adversary chooses everything subject to one restriction, that the host graph is an expander. So the spectral clustering gives an approximate coloring, but the fraction of badly colored vertices is somewhat larger than before, okay? Substantially larger. The local improvement gets an improvement. The fraction of color vertices which are not colored as in the planted is still just proportional to the number of bad vertices as it was before, but the number of bad vertices is much larger than it was before. The cautious uncoloring again gives a safe partial coloring as before, and then we have to finish off with a legal color with dynamic programming, but we need to color now more vertices than we had before, not exponentially small in D, but something could be something like 1/d fraction of the vertices, or even a constant fraction of the vertices. So what's the running time of the algorithm? So the first 3 steps of the take polynomial time just as before, and the only question is about the last step, the dynamic programming. Does it take polynomial time or not? And we already colored correctly most of the graph, exactly as in the planted coloring, almost all the vertices. So how difficult can it be to color just the remaining set of vertices? So here we have a hardness result. So we show that even if the host graph H is not an arbitrary expander or chosen by an adversary, even if it's a random G and D graph, so random graph, and the planted coloring is balanced, so each color is the same, but an adversary may choose it, then recoloring the resulting graph is NP-hard. You cannot complete this last step in polynomial time. And our proof requires certain conditions on the host graph. So our proof applies only to the case where the host graph has degree n to the delta for delta smaller than half and above 2/5. Okay, that's what we know how to prove. Above it, it may be easy. Below it, it may be easy. But it's NP-hard in this region. And what's nice about this result is that it's one of those rare examples in which you can prove NP-hardness for instances which are mostly random. So the host graph was random, so almost all the choices are random. Okay, the adversary could choose the planted partition, but that's not that many choices compared to putting in all the edges. And still you can prove hardness result not under the assumption that some other random problem is hard, but really under some worst case assumption. So here's a sketch of the proof. So suppose that there is an algorithm that recolors the graph G generated from any random G and D graph H, and in which an adversary plants a recoloring, not a random one. Suppose there was such an algorithm. So what we'd like to do, suppose that Q is some small graph that we want to recolor, let's say, and suppose that it comes from some class of graphs that it's NP-hard to recolor. Then what we'd like to show that the algorithm would also color this small graph Q for us. Okay, because it can color this model, it can also color this.
So
And the question is why? Okay, why would it do it?
Q would be picked worst case.
Yeah. So we can pick any Q that we want and give it to our algorithm, and it will color it for us. So, and the question is, why would it do it? So the idea is, of course, to trick the algorithm to think that Q is part of some larger graph that was generated according to the hosted graph model. So the way we do it, we give the algorithm, don't ask it just to color Q, but ask it to color something else Q. And so this is a small graph. And next to it, a random graph on n prime vertices. So n prime is n minus the size of Q, of average degree D, in which we planted a random recoloring. We give it as input to our algorithm and hope that it would, okay, this looks to it exactly what the model should give. This doesn't, but it's small. So we thought when it colors this, it would also color this for us. Why would it do it? So the algorithm, what we're trying to fully to think, is that really the instance that he's seeing came from a larger instance that looks something like the following. So this part, which is now 3-colorable, originally was just a random GN graph, GN prime D graph without the planted 3-coloring. Q was sitting here, and it was part of this large graph. It was connected to it by additional edges. And what we wanted to think is that once we planted a coloring here, so inside Q we planted just the original 3-coloring of this graph. It's not that we planted it, it's an adversary that knows everything did it for us. We planted it in such a way, we planted here a coloring in such a way that all edges going from here, this color class, to this side of the graph, all of them, we colored them exactly the same color as here, and hence all these edges were dropped, and likewise here and here. And the reason why we got this graph here is because we started from this graph and some edges dropped. And that's why we got this graph. So in a bit more detail, so we have some 3-colorable graph, or we think that it's 3-colorable and we want our algorithm to color it for us on n to the epsilon vertices, a small one. So the adversary, So what would the adversary do? On input H from the graph from the class GND, it will find a copy of this small graph in H, plant in H a 3-coloring agreeing with in such a way that edges between Q and the rest of the graph would drop. And in the simulation, what we give the algorithm is just a disjoint union of this graph, small graph Q, and the random graph. And I don't have much time, but the main thing, so Q cannot be too sparse, because otherwise it would not be NP-hard, and it cannot be too dense, because otherwise this would not work, it would not be contained in H. And the main lemma that we prove, that the graph obtained by these two different processes, one is what the adversary does, and one is what we do in the simulation, that these two things are statistically indistinguishable, not computationally indistinguishable. I mean, the stronger notion, they really look the same. So this is not a non-trivial proof, and this is the main source of the hardness result. So let me just summarize. So these were the results known prior to our work. So when we have a random host graph and a random planted coloring, the algorithm of Alon-Kahale could find the coloring. And we ask what happens if there's an adversarial planted coloring and adversarial host graph, which is an expander. So if we just look at finding approximate coloring, then spectral techniques suffice in all these cases. If we look at safe partial colorings, which is a stronger notion, still everything works. And the interesting things begin once we want to complete it to a legal coloring. So this I did not show. If the host graph is adversarial and the planted coloring is adversarial, it's NP-hard for all degrees essentially. And the interesting thing happens when the host graph is random and the planted coloring is adversarial. Here, when the degrees are larger than, I didn't show it here, n to the 2/3, you can find the coloring. When they're between n to the 0.4 and n to the half, it's NP-hard, and in these regions we don't know. So I'll finish with open questions. So are there polynomial time 3-coloring algorithms for the following settings? So one is the following. Let's say that the host graph is a random GND graph with D roughly n to the 1/4 below where we could prove NP-hardness, and the planted 3-coloring is adversarial. So this is one open question that we don't know how to prove. Our techniques for proving NP-hardness completely break down because at this density, at higher densities, we could show that the host graph contains as a subgraph graphs which are hard to color Any specific graph that I want, if it's small enough, is a subgraph of such a host graph. Once the density is so low, like n to the 1/4, then it's no longer true. So we don't know. And the other question, which I think is even more interesting, is the following. Suppose the host graph is arbitrary. Adversary can choose it any way it wants. And the planted color, recoloring is random. So for example, the host graph by itself could be three-colorable, that's okay. But then you plant in it a random three-coloring. So you partition the vertices into 3 random classes and remove edges within each class. Can we color such graphs? So as a reminder, what we can do is if H is not arbitrary but an expander, we can do it. If H is arbitrary but of large enough degree, think of degree, let's say linear degree or maybe n over log n, we can also do it. But in general, it seems unlikely that we can do it, but we don't know how to prove that it's hard. I'll end here.
You get some sort of strange monotonicity if I add edges to H. That only increases the expansion.
Yes.
And so it still remains doable. It was doable before. And if you subtract edges, that helps in the coloring, but the expansion goes down, right? Is that right? Am I right?
So you mean, are you referring
I take a
to,
random graph, G and D.
are you referring like to this area here that is a bit strange?
No, maybe both random,
Yes.
where it's easy, but now I want to do semi-random. I mean, no, you want
Okay.
semi-random.
So we didn't get to semi-random here. I mean, this model has an adversary built in as it is.
Right.
So
The random part, if I do semi-random, if I subtract edges, then the algorithm doesn't work anymore necessarily, right?
so let's say what we did now, maybe for convenience, but I'm not sure we have to think how these things extend. We talked about graphs which are either regular or nearly regular, which makes the spectral analysis, let's say, simpler. It's enough to look at the adjacency matrix. You don't have to look at things like maybe the Laplacian matrix or some other matrix which works better when graphs are not regular. So what you're talking about introduces these irregularities also. So we didn't get there yet. Okay, we didn't.
I mean, to follow up on Rabbi, if you add those edges completely randomly, uniform, then it doesn't.
Then it doesn't matter. They don't hurt you. Though technically, if you look, this is somewhat interesting that the results here, that if you start from a graph which is relatively, usually you would think that the sparsest the host graph is, the more difficult it is to color. But we don't know how to prove it. So it could be that in this region it's easy to color. You add random edges and it becomes difficult to color. Just between color classes. Even random edges might hurt you. We don't know.
Would it make sense to consider this model for, say, 3-sat? So you have maybe some interaction network among the variables, and then you plant the solution and delete. Does it?
Yeah, so you can think of other problems within this model. So let's say a random 3CNF formula would be something like, our model would say start with an arbitrary 3CNF formula. Maybe you want to enforce some expansion conditions or something on it. And then an adversary, for example, or at random, you pick a satisfying assignment and throw away all the clauses which are not satisfied by it. So yeah, so this model can be applied to many problems. Yeah.
So here I'm assuming you're using constant expansion for the
Yes.
book. Does it degrade gracefully with the amount of expansion? Is it,
So the point here was, in a sense, So one thing, if you would just want to do the thing most close to random graphs, would take the second eigenvalue to be square root t, much smaller. So one of the points of this work was to show that you really don't need such good expansion. It's still very good expansion what we are taking, but not as good as you have in random graphs, much worse than random graphs.
No, but if the,
And then the question is what happens as the expansion degrades. I'm sure that there's some trade-off involved, but we didn't work it out.
Let's have one more question while the next speaker sets up so we can stay on time. Let's do the testing hands. Do you want to just come forward and okay. I'll leave it to
So
you.
I'm curious, I mean, your NP-hardness result is a worst-case result.
Yes.
How difficult do you think, or how unlikely is it to actually get such a graph if you look at distributions that have been studied before? Are they all very weird, or do they just tend to be hard? In this regime where you show the NP-hardness.
So for the NP hardness, the thing that we used is that the adversary chooses the planted coloring. I'm not sure that people looked so much at these versions where the adversary makes this choice.
So I
And
guess
the point was to show, I think, that if you give him this choice, he doesn't need anything else. That's enough to make the problem difficult, even if it's a random graph. So
I guess what I'm asking is it difficult to construct such an adversary, right? So how hard does the adversary?
no, the adversary has to solve NP-hard problems to generate these instances.
Right.
So
Great. Well, let's thank Uri again.